Hello, my name is Alex Jung, and in this video, I'm going to present the paper entitled Clustering in Partially Labeled Stochastic Block Models via Total Variation Minimization. This paper has been accepted for presentation at the Asiloma conference in 2020. You can find a preprint of this work on arXiv. And I would like to explain our work with the help of an illustrative application domain given by a social network. So this simple social network consists of individuals who are related by social ties or friendships. Each node representing an individual has also many properties. Modern sensor and information technology allows to collect us tons of digital data about individuals. However, in this work, we consider maybe the simplest setup where each individual is characterized by a single property or label. And in this toy example, the label of an individual reflects if the person is a cat person or a dog person. And we assume that an individual is either cat or dog person, but cannot be both. In general, we do not have access to the labels of all individuals, but only to a few of them. For example, we can only get labels by asking people within a survey, and surveys cost money, so we typically cannot afford to survey the entire social network. So we collect the nodes, a few nodes for which we know the labels, into a training set. And our goal, or the method that we develop or analyze, is then inferring or predicting the labels of all individuals based on the social network structure and the few known labels on the training set or labeled set. And what makes this approach useful or feasible, let's say, this approach is feasible because we assume that well-connected subsets or blocks or clusters of individuals tend to have similar properties or preferences. So in this case, we assume that dog persons are typically friends with other dog persons and not with cat persons. To quantify or to study the performance of our approach, we use a simple generative model for the network structure. Maybe the most basic probabilistic model for clustered networks is the stochastic block models. Within a stochastic block model, we assign each node a block index, which corresponds to the label C in our case. And we then connect two nodes with the same label or within the same block with some probability P in. And on the other side, we connect nodes with different block indices or different label values C with a much, much smaller probability P out. Yeah, in this work, we assume that these two parameters, P in and P out, are given. So these are fixed model parameters of the stochastic block model. In general, we might need to estimate them from data using some inference method, but this is without the scope of this paper. We have now arrived at formulating the application as a learning problem within a partially labeled stochastic block model. And this problem has been studied before already in statistical physics, which resulted in some heuristic methods for recovering the labels of the entire network. These methods are often based on approximations or limits of limit considerations that assume the network to be infinitely large. In contrast, we consider a finite network size, and we use convex optimization methods to learn the labels in a partially labeled stochastic block model. And by relying on convex methods, we can use a powerful toolkit for the analysis and the design of efficient convex optimization methods. So in order to formulate this learning problem, or to formulate partially labeled stochastic block models within signal processing, we assign each block an indicator signal. So each block is assigned one individual or one separate indicator signal. And the values of the indicator signals, they represent, or somewhat, they model the probability that a certain node belongs to the block C, for which we consider the indicator signal. And then learning in partially labeled stochastic block models becomes a signal recovery problem. So learning the blocks or learning the clusters amounts to, or is equivalent to, recovering the indicator signals for each block. And we have one separate recovery problem for each block. So we can do this in parallel. So let us flesh this out for our cat and dog social network. So here we have two blocks or two clusters, one cluster of dog persons and one cluster of cat persons. And if we want to learn or identify the dog cluster, we have to learn the indicator signal for the dog cluster. So this indicator signal has some known signal values. For some persons where we know it's a dog person, we set this indicator signal equal to 1. Whereas for some persons for which we know that they are not dog persons, or which means cat persons, in this simple example, we set the signal value to 0. And then learning the block amounts to recovering the entire graph signal or indicator signal for the dog persons. And we do the same completely independently for cat persons. So we have to recover the indicator signal for the cat person cluster. So let's now consider the recovery problem for a particular block. For example, for the dog person block. And this recovery problem uses the fact, or is based on the property that clusters have a small number of edges leaving the cluster. So in other words, the clusters have a small boundary. And this small boundary property translates into the signal processing property of a small total variation. So learning the indicator signals for the blocks amounts to a total variation minimization problem, where we fix the graph signal values for the individuals where we know the labels. So either it's equal to 1 if we know it's a dog person, or it's equal to 0 if we know it's a cat person. And for all other nodes, we let this total variation minimization work or recover the signal values for all nodes where we don't know the label. Okay, so as can be verified rather easily, this total variation problem or total variation minimization is a convex optimization problem. It's a non-smooth convex optimization problem because the objective function is the non-smooth total variation. And it has an appealing structure that allows to apply a primal dual method for convex optimization. And this primal dual method is attractive in particular for big data applications, as it can be implemented as a message passing over the data network or social network in this case. And what is more, this primal dual method is also quite robust in the sense of having a performance that degrades only gracefully with the amount of any errors that is introduced in the update. So this primal dual method is an iterative method, which consists of repeating some updates. And these updates involve often in real hardware some numerical errors like rounding errors, or also hardware failures where nodes, the link between nodes can be failing, and the communication or the message passing cannot be implemented perfectly. And this primal dual method is quite robust against such imperfections. So I have written down here the pseudocode for this primal dual method. And these updates can be implemented as message passing updates. So this amounts to a message passing protocol, which is highly scalable. And the main theoretical result of this paper is a precise characterization of the stochastic block model parameters, such that this total variation approach successfully recovers the true underlying blocks. And this analysis is based on the fact that, or on a sufficient condition for total variation minimization to work, based on the existence of flows. So we have shown in our earlier work that total variation minimization is accurate, or accurately recovers the cluster structure of a network if we can, or if there exists a flow, a network flow over the data network, such that all boundary edges with capacity 2 are saturated. So they have exactly a flow of value of 2, whereas the intra-block edges are not saturated and having capacity of 1. It can be shown that if we can find such a flow, such that the boundary edges are saturated, then the solution of total variation minimization is the true clustering, or the true cluster structure. And we use the basic properties of stochastic block models to bound the probability that this is possible. So the derivation uses standard tools from large deviation analysis or concentration bounds and spectral graph theory. I will not go into details, but rather show here our final main result, which is a sufficient condition on the SBM parameters, P in, P out, and the number of labeled nodes that we have per block. So we assume that for each block, we know S individuals. So we know S cat persons, and we know S persons where we know that they are dog persons. And our condition indicates that the relevant quantity is, so for fixed block sizes, so in this condition also the block size enters, how many nodes are in each block, but for fixed block sizes, the relevant quantity that determines if total variation minimization works is the product of the number of labeled nodes per block times the ratio of the probabilities, of the edge probabilities. And this condition, or the insight that this is the relevant quantity, is also confirmed by numerical experiments, where we plot the accuracy as the number or the fraction of correctly labeled nodes as a function of this product of number of labeled nodes per block, S, times the ratio of the probabilities. And we clearly see here a phase transition. So these curves, they are obtained for different choices for number of labeled nodes per block. But if we scale this number of labeled nodes per block by the ratio of the SBM probabilities, we make these curves lay on top of each other, which confirms our insight that the relevant parameter is the product of the number of labeled nodes per block, S, times the ratio of the probabilities. Okay, so to wrap up, we have formulated learning of partially labeled stochastic block models as a convex optimization problem, which we solve using an efficient primal dual method for convex optimization. This method is highly scalable, as it can be implemented as message passing. It's guaranteed to converge, and it's robust against errors introduced in the iterations. And our main theoretic results is a precise characterization of the parameters of the stochastic block model such that total variation minimization correctly recovers the cluster structure.